All right, today we are diving into one of the most brilliant, most important ideas in modern history. Seriously, it's a mathematical trick that secures our entire digital world, and it all kicks off with a question that sounds completely impossible. So, think about this for a second. It sounds like a riddle, right? How can two people, let's call them Alice and Bob, agree on a secret key if someone, we'll call her Eve, is listening to every single word they say? It feels like it can't be done, but it's not magic, it's just really, really clever math.
So, to get our heads around how this works, we're going to start with a really simple analogy that you can picture in your mind: mixing paint.
This right here is the absolute key. We need a trapdoor. Think about it. Mixing blue and yellow paint to make green? Super easy. But have you ever tried to unmix green paint? To pull the pure blue and pure yellow back out? It's basically impossible. We need to find a mathematical process that works just like that. It's a one-way street. Okay, so this one-way trapdoor idea, well, you can't really do it with the kind of math we use every day. We have to step into a totally different world, a special playground called modular arithmetic. But, to keep it simple, we're just going to call it clock math. So this is the crucial difference. You've got the normal number line we all learned in school, which just goes on forever. But in clock math, you're working in a closed loop. Once you hit a certain number, you just wrap right back around to the beginning. And this one little change has massive consequences. It completely scrambles predictable patterns. You already know how this works. Think about a 12-hour clock. If it's 10 o'clock and you wait 4 hours, it's not 14 o'clock, right? It's 2 o'clock. Why? Because 14 divided by 12 leaves a remainder of 2. And in clock math, the only thing we care about is that remainder. The point where you wrap around, in this case 12, is called the modulus.
And this is just a perfect illustration of that pattern scrambling I was talking about. Normally, y equals x squared is this beautiful, smooth, predictable curve. But look what happens when you graph that same exact formula using clock math. It just looks like a mess of random dots, like static on an old TV. That wraparound effect completely destroys the pattern and hides the relationship between the numbers.
So it's this scrambling effect that finally gives us the perfect one-way trapdoor that we've been looking for. And this gets us right to the heart of it. The huge difference between an easy problem and a nearly impossible one. Okay, look at the problem on the left. In the normal world, this is easy. 2 to what power equals 8? We all know that's 3. Simple. But now, look at the problem on the right in the world of clock math. 2 to what power when you divide it by 11 leaves a remainder of 5. Because all the patterns are scrambled, there's no simple trick. The only way to solve this is to guess. You have to try 1, then 2, then 3, all the way up until you happen to land on the answer. It's just guess and check. This is called the discrete logarithm problem. And this is the absolute genius of it. The fact that this is so hard to solve isn't a flaw. It is the feature. It's our trapdoor. It's our unmixable paint. We've found something that's easy to do in one direction, but unbelievably hard to reverse. So now we have it all. We have our unmixable paint, we have our clock math, and we have our trapdoor. We can finally put all the pieces together and actually perform the trick. It's called the Diffie-Hellman key exchange, and you can think of it like a secret handshake that's done completely out in the open. Here's how it works. First, Alice and Bob publicly agree on a starting number and a modulus, the size of their clock. Then, they each pick a private number that they keep completely secret. Next, they each mix their own private number with the public one and share those results out in the open. Now here's the magic. Alice takes Bob's public result and mixes it with her private number. Bob does the same thing with Alice's public result. And bam. Because of how clock math works, they both end up with the exact same final number. That's their shared secret. And Eve, who's been listening the whole time, is completely stuck with that impossible discrete logarithm problem. Now, this isn't just some cool math puzzle. This secret handshake is the bedrock of our digital lives. It's what lets us do everything securely online, from banking to just sending a message. The whole reason this is so secure comes down to one thing: scale. In our example, we use small numbers like 11. In the real world, cryptography uses numbers that are thousands of bits long. A 2048-bit number is, well, it's ridiculously huge. It's a number with more than 600 digits. And because the numbers are that big, the guess and check method becomes totally impossible. The number of possibilities is so mind-bogglingly vast that even the fastest supercomputer in the world would be guessing for trillions of years. That's what we call cryptographic hardness, and it's the lock that keeps your digital life safe.
So the bottom line is, you rely on this amazing piece of math every single day, probably without even thinking about it. Every time you see that little padlock in your web browser, it means your computer just did this secret handshake with the website's server to build a secure connection.
This beautiful idea from the 70s has kept us safe for decades. But the story isn't over. People are always looking for new ways to break things, and future technologies like quantum computers might one day be able to solve this hard problem easily. So right now, there's a race to invent the next generation of trapdoors, the next kind of unmixable paint. What will that new math look like? Well, that's a question everyone is trying to answer right now.